Okay guys, so here's the homework question. I'll go through it as quick as possible. It says prove that 3 to the power of n is greater than n squared when n is greater or equal to 2. Okay, so the first step, we're going to prove for n equals 2. Okay, because n is greater or equal to 2. So 3 squared is greater than 2 squared. And 3 squared is 9. And 2 squared is 4, so that is true. So step 2, we're going to assume true for n equals k. So I'm going to put in k for n, and I'm going to assume that is true. Step 3, I'm going to take this, step 3, prove true for n equals k plus 1. Okay, so I'm going to take this and I want to make this 3k plus 1. So what do I have to do? Well, if I multiply it by 3, multiply this by 3 then as well, okay, do the same to both sides, I can change this into 3k plus 1. It's greater than 3k squared. Okay, so I'm going to call that a and that b. I know a is greater than b. Problem is, this, fair enough, is greater than that, but that is not the same as that. That's not a k squared. What I want to prove is that 3k plus 1 is greater than k plus 1 squared. Okay, because that is when I put in the k plus 1 for n. That's not doing that for me. However, if I look up here, if I put in the k plus 1 in place of k here, call that c. Now that is that. That is that. So there's a, there's c. Okay, so what we're saying here is a is greater than b. I want to prove that a is greater than c. Okay? I want to prove that a is greater than c. If I can prove that b is greater than c, well, a then must also be greater than c because it's greater than b. Alright, so here I have it over here. Okay, so let's start proving it. I want to prove that b is greater than c. So b is 3k squared, and I want to prove that that is greater than k plus 1 squared. Okay, so here we go. 3k, k squared is greater or equal to, well, k plus 1 squared is k squared plus 2 k plus 1. Okay, bring it all over to one side and we get 3k squared minus k squared is 2k squared. If we bring that over, it'll be minus 2k, and if we bring that over, it'll be minus 1, and that is greater or equal to 0. Okay, right. What I'd like to do now is the completing the square method. Okay, but I can't because of this 2. So what I'm going to do is I'm just going to take that 2 out, and 2 into this. If I divide 2 into that, I get k squared. If I divide 2 into that, I get k. And if I divide 2 into that, I get half. Okay, that is not nice, right? But that's just unfortunately the way it is for this question. Okay, so I'm going to complete the square here. So I'm going to put a 1 there, it might make it easier now. I'm going to half the middle term and then square it, right? So watch. Now this 2 doesn't really matter, but I may as well keep it in anyway. So I have k squared minus 1k. Half the middle term, I get minus a half. Squared, I get plus a quarter. Okay, but I already have a half here, So I have minus a half, and I have to take away that quarter as well, so minus a quarter, and that's greater than 0. Okay, nearly there. So 2, now I can take this, I can make a perfect square out of it, so that'll be k minus a half squared, and then minus a half minus a quarter is minus 3 quarters, and that should be greater than 0. Now, we're after saying for when n is greater or equal to 2. So put 2 in for k. C is greater than 0. Yeah, so put 2 in for k and see if it's greater than 0. It is. Okay. If you want, you could put 3 in for k as well and see if it's greater than 0. It will be. In fact, if I put in any number here, okay, 2 or greater, this is going to be positive, and that is not going to make the sum negative. Okay, so any number I put in here that's 2 or greater will make this positive. So again, I'm not going to finish it off for you, but if you put 2 in for k, show that it's greater than 0, and then say therefore 3n is greater than n squared when n is greater or equal to 2. Okay? Right. Okay guys, the questions we had today. So there's the first one. Okay, it says prove that 1 plus 2 plus 3 plus all the way up to whatever number we want can be shown as n brackets n plus 1 over 2 for all natural numbers. So step 1, prove for n equals 1. Okay, so that would be 1 equals 1, go in for n, 2, and that was 1 equals 1 plus 1 is 2, multiplied by 1, multiplied by 2, and 1 equals 1. So that is true. Step 2, assume true for n equals k. Okay, so 1 plus 2 plus 3 plus all the way up to a given number, whatever that is the same as whatever that number is, that last one, multiplied by whatever that number is, plus 1 over 2. We're going to assume that's right. And then step 3, we're going to prove for n equals k plus 1. So we take the left hand side first, 1 plus 2 plus 3 plus all the way up to k, which is the second last number, plus the next number, and I'm going to show that that is the same as anywhere see n here, I will put in k plus 1. So k plus 1, and then k plus 1, put a different bracket around that, plus 1 all over 2. Okay, so let's just see what I'm after doing there. So where the n is, there's a k plus 1. Where the n is, there's a k plus 1, and there's also a 1. I just put these extra brackets around it to keep it, I suppose, a bit neater and more together, all over 2. Right, so now when I look and I see that here I have 1 plus 2 plus 3 all the way up to k, I can actually replace that with this, because look, 1 plus 2 plus 3 all the way up to k is this. So I'm going to do that. So k plus 1 all over 2. Okay, so I've replaced this with that. I also have the k plus 1 over here. And hopefully that will equal k plus 1, k plus 1 plus 1 all over 2. And I just need to start tidying this up and simplifying it using a bit of algebra to see if this can equal this. Right? So first of all, we have a little problem in that this is over 2, but this is not over 2. So I am going to try to make this over 2, or give it a denominator of 2. So we have the k plus 1 over 2 plus, now I'm going to put this over 2 and the k plus 1, but by putting it over 2 I'm after dividing the whole sum by 2. So in order to, I suppose, undo that, I'll have to now multiply it by 2. So now that is the same as that. And I'll simplify this a bit. K plus 1 is just k plus 2. And that's all over 2. Alright. This I can put it all over the single 2 again. So we go k by k squared plus k by 1 is k plus 2 by k is 2k plus 2 by 1 is 2, and that equals, and we multiply out the brackets and we get k by k squared, and k by 2 is 2k, and 1 by k is k, and 1 by 2 is 2, and that's all over 2, and we're nearly there. Simplify this, k squared plus 3k plus 2 all over 2, and this simplified is k squared plus 3k plus 2 all over 2. They are equal. Sorry, no. They are equal. So I'll say, therefore, 1 plus 2 plus 3 all the way up to n can be shown as n plus 1 over 2 for all n is an element of n. Okay, so that's that done. Next one, prove that a to the power of n minus 1 is divisible by 7. Okay, so first step, prove for n equals 1. So a to the power of 1 minus 1, a to the power of 1 is 8 minus 1, which is 7, so that is true. Step 1. Step 2, assume true for n equals k, and that will be 8k minus 1. Assume that's true. And the third bit then is prove for n equals k plus 1. And remember these divisibility ones, we will look at this method. We'll go the f k plus 1. So the last number minus the second last number equals, well, we'll take this and we put in k plus 1 first. So 8 k plus 1 minus 1, so that's that, because we put k plus 1 in for the n, minus, we keep this in brackets, the f of k is here, or another way of saying it, we'll just put the k in for this, so we have 8k minus 1. Quick bit of algebra then, we have 8k plus 1 is the same as 8 times 8k minus 1 minus 8k, and then minus by minus plus 1. That'll equal the 8 times the 8k, minus 1 plus 1 is gone, minus 8k. Okay, then we will take this from this. We have 8 8k's here, and we're minusing 1 8k, so we're left with 7 8k's. So what that is saying is the jump, or the difference between the last number and the second last number is 7 8k. Now, is that divisible by 7? Yes, it is. So the first number is divisible by 7, and every jump is also divisible by 7. So that straight away there's a proof that for every number here we put in here, it will also be divisible by 7. Okay, remember we talked about that. If the first number is divisible by 7, and the jump to every next number is also divisible by 7, well then every number has to be divisible by 7. But let's just tidy this up a bit. Let's not have, I suppose, the marker having to, I suppose, figure out what's going on. Let's make it very clear to him. So what we're saying here is the last number minus the second last number is divisible by 7. But let's not have the corrector, needn't even think here. I'm going to prove beyond a shadow of a doubt that the last number actually is divisible by 7. Here's how I do it. I'm going to get rid of this. I'm going to get rid of this f of k. I'll do that by adding f of k to this side. And if I do, I will get just the last number. And over this side then, I will also add f of k. But this time I won't just write in f of k, I'll write in actually what it is. And it's this, okay, when I just put k in. So I have plus 8k minus 1. Now we're going to ask ourselves, is this divisible by 7? Yes. Is this divisible by 7? Divisible by 7, and why is that? Because it's assumed. So the last number is made up of two parts, and both are divisible by 7. Well, in that case, so therefore f of k plus 1 is, sorry about the not neatness of it now, divisible by 7. Okay, so that's divisible by 7. But really what we're going to say is, therefore, the 8n minus 1 is divisible by 7. Okay? Right, last one, lads. Rewrite this. 2n. Okay, last one, so. Step 1. Sorry, I think that was, oh yeah, when n is greater or equal to 3. Okay, so step 1, prove for n equals 3. Okay, not 1, 3, because there it is. So we have 2 to the power of 3 is greater than 2 times 3 plus 1. 2 to the power of 3 is 8, and that's 2 3s are 6, and 1 is 7. So that is true. Step 2, assume for n equals k. So we have 2 to the power of k is greater than 2 times k plus 1. Okay, step 3. Prove for k plus 1. For n equals k plus 1. Right, so again with these inequality ones, we will take this 2k is greater than 2k plus 1. Big with brackets in there or not, doesn't matter. Right, and now I want to turn this into a 2k plus 1. And how do I do that? Well, I multiply it by another 2. But if I do that, I'm going to have to multiply all this by 2 as well. So now I can change this to 2k plus 1. And this will be 4k plus 2. Now, what I want to prove is that this is greater than this. Okay? Or another way of saying it, well, this with the k plus 1 here is greater than 2k plus 1 plus 1. Alright? But I have only proven that this is greater than this. Now this 4k plus 2 is not 2k plus 1 plus 1. So I'm going to call that B. Now let's look over here. We have the 2k plus 1. Alright. Now if I change that to 2k plus 1 plus 1, alright, we call that C. because that really is that. I'm putting in the 2 k plus 1 instead of n. If I can prove that b is greater than c, then by default a is also greater than c. So 4k plus 2 is greater than 2k plus 2 plus 1. Okay, I'm going to multiply that, 2 multiplied by k, 2 multiplied by 2, and then another 1. 4k plus 2 is greater than 2k plus 3. Now we start bringing things over and we get 2k minus 1 is greater than 0. And we're going to check for 3. So we put 3 in here. Sorry, again you can't see it. Sorry. Okay, so we're going to put 3 in here because it said for n is greater or equal to 3. So we'll see if this works if I put in 3. So we have 2, 3 minus 1 is greater than 0. Is that true? Well, we have 6 minus 1 is greater than 0. So 5 is greater than 0. It is true. And to be honest, if I put in 4, it's going to still be greater than 0. If I put in 5, 6, 7, if I put in any number, it's always going to be greater than 0. So I would say, therefore, 2n is greater than n plus 1 when n is greater or equal to 3. Okay? Thanks, that's